Hello class. In this lesson sequence, we are continuing our study of solution stoichiometry. In our last lesson, we discussed precipitation reactions and the different ways to represent them using balanced chemical equations, complete ionic equations, and net ionic equations. We also briefly discussed gravimetric analysis, which is a laboratory technique used to measure out and analyze a precipitate formed during a reaction. So here, let's do some calculations. This problem in exercise 9 says calculate the mass of solid NaCl that must be added to 1.50 liters of a 0.100 molar silver nitrate solution in order to precipitate out all of the Ag plus ions to form AgCl. Essentially what this means is that we have a solution of silver nitrate and we want to react to completion to use up all of our silver. So we have solid sodium chloride plus AgNO3, which is aqueous, and we're told that our precipitate that forms will be AgCl. That must mean the other component has to be sodium nitrate. Nitrate and sodium salts are aqueous, so we can assume this one will be aqueous as well. Thankfully, when we balance, it is 1 for all of the coefficients. Now, before we do any calculations, keep in mind from your net ionic equation, the relevant parts that we care about are Ag and Cl because they react to form AgCl. So those are the components we'll need to focus on when doing our calculations. To start this problem, we are given liters and a molarity. If you remember your manipulations of the molarity equation, when you multiply liters times molarity, you can find moles. So we will need the moles of AgNO3. Need moles of AgNO3 to find the moles of NaCl, and then we can find the moles of the grams of our sodium chloride needed. So that's essentially our pathway here. So 1.50 liters times 0.100 molar AgNO3 gives us 0.150 moles. 0.150 moles of AgNO3. Now, technically, we want all of the Ag ions to be used up in this reaction. Now, when we look at AgNO3, there is 1 mole of Ag plus for every 1 mole of AgNO3. Keep in mind, some of these problems, you're going to have to pay attention to the stoichiometry of the ions compared to the ionic compound. In this one, it does not matter because they are 1-to-1, but sometimes that will be an issue you'll have to keep track of. So we can essentially assume that this is also equal to 0.150 moles of Ag plus. So if we're thinking of a net ionic equation, moles of Ag plus, moles of Cl minus reacts to form AgCl. 0.150 moles of Ag plus and we use that mole ratio of Ag plus to Cl minus, 1 mole of Cl minus, tells us that we need the same amount of moles here, 0.150 moles of Cl minus. Similar principle to what I just described above with Ag plus ions, there is 1 mole of Cl minus for every 1 mole of NaCl. So this is also equal to our moles of NaCl. So then we just need to convert moles of NaCl to grams of NaCl. So our molar mass of NaCl, 58.44 grams per mole. And then we're going to multiply that to get the mass of 8.766 grams. We have to keep track of our sig figs. We had 3 significant figures with our liters and 3 significant figures with our molarity. So we are at 3 significant figures for our final answer. So 8.77 grams of NaCl is needed to precipitate out all of our solid. And that is at 3 significant figures. Okay, let's do another one. This time we have an aqueous solution of sodium sulfate and aqueous solution of lead nitrate mixing to form lead sulfate. And we want to calculate the mass of lead sulfate formed, and we're given the liters and molarities of both of our reactants. So when you have liters and molarity of both reactants, this is going to turn into a limiting reactant problem. So first thing we should do is figure out our moles of each of our starting components. Oops. If we get everything into moles, it's just easier to work with. And then I'm also going to put the work for the other one up here just so I have some space. 2.0 liters times 0.0250 molar Na2SO4. All right. And I don't need to really worry about sig figs until the very end here of the problem. All right, so 0.0625 moles of lead nitrate, and then 2.0 times 0.0250, 0.05. So this is 0.0625 moles of lead nitrate and 0.05 moles of Na2SO4. All right, and I want to know how many moles of lead sulfate will precipitate. So for this, I should focus on the ions. So if I know the moles of sulfate ions and the moles of lead ions, then I compare to figure out which one will run out first. I know that lead 2 plus aqueous reacts with sulfate 2 minus aqueous to form lead sulfate. And eventually I want to know the mass of lead sulfate. So I have 1 mole of lead for every 1 mole of lead nitrate here. So just to show the work, 0.0625 moles of lead nitrate, 1 mole of lead nitrate is equal to 1 mole of lead 2 plus ions. So those are equal amounts there, 1-to-1 ratio. And then I can do the same thing with the sulfate ions. 0.05 moles of sodium sulfate are present, and there's 1 mole of sodium sulfate for every 1 mole of sulfate. So then I also have 0.050 moles of sulfate. It's very clear, since this is a 1-to-1 ratio, that this will run out first. Since sulfate runs out first, think of this like a BCA table, which we talked about back in the limiting reactants. I can subtract 0.05 moles from each of these. Sulfate is my limiting reactant. That goes down to 0. And then that means if I started with no moles of lead sulfate, I must end up with 0.050 moles of lead sulfate. So then we're not asked for what's left over in terms of lead ions, but you can figure it out. It's good practice. So we're left with 0.0125 moles of lead ions remaining. Moles of Pb2+, we're going to say in excess. Remember our good vocabulary. All right, and now we can multiply by our molar mass, 1 mole of lead sulfate, and then we need to figure out our molar mass of lead sulfate. So lead has a mass of 207.2 plus 32.07 for sulfur, and then 16 times 4 for your oxygen. The mass is 303.27. 303.27 grams of lead sulfate per mole. And then we're going to multiply that by our moles of 0.05. And with sig figs, it looks like we had 3 significant figures for each of our volumes and 3 significant figures for each of our molarities. So we should round our answer to 15.2 grams. So 15.2 grams of solid lead sulfate will form when you mix 1.25 liters of 0.0500 molar lead nitrate with 2 liters of 0.0250 molar sodium sulfate. Okay. There are a couple of problems in You Try It Set 9 for you to try using the exact same process. Let's check our time. Okay. On to acid and base reactions. So acid and base reactions are very similar to precipitation reactions, except instead of forming a solid, we are going to form a salt. An acid is any compound that upon reaction with water produces an ion called the hydronium ion, or H3O+, and a corresponding anion. A base is any compound that provides a hydroxide, or OH-, and a cation when dissolved in water. There is one exception you need to memorize, and that is ammonia. I mentioned that a while back, but that is a classic weak base. It reacts with water to form NH4+, the ammonium ion, and OH- in solution. A neutralization reaction is when we mix acids and bases together to neutralize each other. The moles of acid are equal to the moles of base in a neutralization reaction, and it is also equal to the moles of salt formed. So we'll discuss that process in a minute. Each reactant, one is an acid, one is a base, is neutralized, and the products formed are water because H+ and OH-. H+ comes from the acid, OH comes from the base. When they come together, they form HOH, or if I rearrange that formula, H2O. So they form water, and then their anions and cations react to form a salt, or an ionic compound. The anion from the acid reacts with the cation from the base to form our salt. To do calculations with these, we're going to use the dilution equation, except instead of saying stock versus dilution, we're going to look at MAVA, where A is the acid and volume of the acid, and MBVB, where B is the molarity of base, V is the volume of base. So we're going to set up some balanced, complete, and net ionic equations using very similar principles as we did with our precipitation reactions. They are still going to act as if it's a double replacement reaction, but specifically, H and OH are going to react together, and then the cation and anion are going to react together. So these are going to react to form water, and then the perchlorate ion is going to mix with Mg to form our salt. So I have HClO4 aqueous plus MgOH2, which is a solid, and I will get water, H2O, as a liquid, and MgClO4. I do have to check charges here, +2 and -1, so I needed a 2 on the outside with my parentheses. I should go through and balance my equation. I have 2 perchlorate ions on the right, so I need 2 to balance out on the left. That also gives me 2 H's here. And I also had 2 H's here and 2 oxygens. So in total, I have 4 H's on the left and 2 oxygens on the right. I need to balance out here. So the balance is 2, 1, 2, 1. And I should mention that salts are going to be aqueous in an acid and base reaction, at least as far as we know. So in this particular equation, when things split up, we have a strong acid, strong base. So we end up with 2 moles of H+, which is aqueous, having some technical difficulties here. There we go. And 2 moles of ClO4-, also aqueous. 1 mole of Mg2+, which is aqueous. Oh, I'm sorry. I just saw that magnesium hydroxide is a solid. So when I'm looking at the complete, remember that your solid does not split up. So this is MgOH2 solid. Water does not split up. And then we can leave our aqueous components here. And keep in mind that you have 2 moles of perchlorate here. Okay. So if I look at spectator ions here, this one's kind of tricky. I only have 1 spectator ion, and that's my perchlorate. So when I bring things down here, 2H+ and magnesium hydroxide, solid, react to form 2H2O, which is a liquid, and then Mg2+ ions. So that one was actually a little bit tougher than I had originally intended, but the process is the same. All right, let's do another one. Here we have HCN and NaOH. So again, H and OH are going to react to form our water, and then Na and Cn are going to form our salt. So here we get Na plus Cn minus to form our salt here, and then we get H2O. And if we balance things, everything is actually balanced 1-to-1 on this one. So that's not too bad. Then again, we're going to try and split up our aqueous components. And we're going to get 1 mole of H plus aqueous plus 1 mole of Cn minus aqueous plus 1 mole of Na plus aqueous and 1 mole of OH minus aqueous. And then we form 1 mole of Na plus aqueous, 1 mole of Cn minus aqueous, and then our 1 mole of water, which does not dissociate because it is a liquid. If I check my spectator ions here, Cn minus is the same on both sides, Na plus is the same on both sides. So here, my net ionic equation, and this is usually what you will see as a net for an acid and base reaction, is that H plus and OH minus react to form H2O, which is a liquid. I know the one before was a little bit different because you actually had a solid component as one of your reactants, but it is good to work through that process. So you saw 2 really good examples of some net ionic equations specific to acids and bases. Okay, that I think is about all for this lesson. You have some problems and you try at set 10. There's one more. We can do this one real quick. All right. It's a very similar process. HCl and NaOH. This is one you're going to do in lab a lot. You're going to mix HCl and NaOH in an acid-base titration at some point in AP Chem. So it's good to see this one. And this one, we're just going to make salt, NaCl. And this one is balanced really nicely for you as well when we go through and do everything. And then again, if you were to do your net, everything that's ionic will split apart. You can probably tell what your spectators are going to be here already. It's going to be Cl minus and Na plus. You'll get water undissociated and then Na plus and Cl minus. Again, Cl minus Na plus are the same on both sides. Those are your spectators. So those drop out of your equation, and we get the same ionic equation or net ionic equation as we did as the last one. H plus and OH minus gives us H2O. So again, the key here is that when we're doing an acid-base reaction, we're usually going to have the same net ionic equation. I know there was an exception to that rule with our first problem, but that's generally what we'll see. But it's still good to go through the steps of balanced, complete, and net ionic equation to make sure that you have everything. Okay, that is all for this lesson. Go ahead and try at set 10, and we will pick up with neutralization calculations in the next lesson. Have a good day.